Hello everyone. This class will continue to study the first chapter, Part 2, Content PN Junction. We learned in the previous content that the internal structure of the crystal diode is mainly composed of a PN junction. After understanding the basics of semiconductor physics, we can further learn about the relevant knowledge of PN junction. So what is a PN junction? PN junction is p-type impurity semiconductor and n-type impurity semiconductor, the structure formed by combining the corresponding process. Let's look at the schematic. When p-type semiconductor and n-type semiconductor have such a contact surface, it will form a barrier layer. Let's take a look at the process of barrier formation. When p-type impurity semiconductor and n-type semiconductor are combined, because at both ends of the interface, the mutation concentration is very different. This will cause the diffusion of the pollens. For example, the holes in the p-type region will diffuse into the n-type region. The multi-element free electrons in n-type semiconductors also diffuse like p-type regions. In the process of diffusion, a multi-diffusion current ID is formed, which is expressed by ID. In the process of diffusion, due to the multi-child spread to each other, a large number of the other party's minority children are compounded, and this position near the interface will leave a lot of impurity ions, which greatly reduces the concentration of carriers. We call this region the space charge region. After the space charge region is formed, let's observe the n-type semiconductor. Impurity ions are positively charged. p-type impurity ions are negatively charged. This will form a built-in electric field. The electric field is from positive ions to negative ions, which is the direction. After the built-in electric field is formed, it will further hinder the diffusion of multiples. For example, after the electric field is formed, it will prevent the holes in the p-type region from diffusing into the n-type region. And it will also prevent free electrons from the n-type region from diffusing into the p-type region. And after the built-in electric field is formed, it will cause a minority on both sides to drift, such as holes in the n-type region will drift towards the p-type region. Similarly, in the p-type region, the minority carriers and free electrons will also drift towards the n-type region. And the drift current will be formed during the drift, which will be expressed by IT. Diffusion movement makes the built-in electric field gradually strengthen, and the drift of the minority carrier also gradually increases. At a certain moment, the majority carrier diffusion current ID and minority carrier drift current IT are approximately equal, or when they are equal, our barrier layer forms a dynamic balance. At this time, from a macro perspective, the total current in the barrier layer is zero. The width of the space charge region remains unchanged. We call the barrier layer at this time the PN junction or depletion layer, barrier layer, also call it PN junction. This is a process of PN junction formation and the principle of achieving dynamic balance. Let's take a look at another concept, built-in potential difference. After the PN junction is formed, that is, after the barrier layer is formed, it will have a built-in electric field, from positive impurity ions to negative impurity ions. This barrier has a potential difference between its left and right edges. Assuming the edge of the barrier layer on the p-type semiconductor, potential is zero. We call it in the n-type semiconductor on the right. The potential of this barrier layer is VB, and the potential difference between them is VB. This VB is called the built-in potential difference. For silicon materials, the size of VB is about 0.5 to 0.7 volts. Germanium material is 0.2 to 0.3 volts. We use VB to describe its calculation formula. As shown in this formula, from this formula, we can see that VB and Na, Nd are directly proportional to the doping concentration. One parameter here is Vt. Here we need to emphasize Vt is called thermal voltage. At room temperature, usually take 26 microvolts. In the future, this is when we introduce the characteristics of diodes or transistors, a parameter to be used frequently. We can use it as a constant to take Vt at 26 microvolts at room temperature. When calculating it can be used as a constant. Everyone needs to remember this. This is a built-in potential difference. Let's take a look at the volt-ampere characteristics of the PN junction. Volt-ampere characteristic is the main characteristic of PN junction. It actually describes the relationship between the current on the PN junction and the voltage across the two ends. When the applied voltage is positive, we call it forward characteristic. When the external voltage is negative and reversed, we call it inverse characteristic. First, let's look at the forward characteristics. The PN junction in this picture is a diode. Apply external power supply forward voltage. P-type area connected to the positive pole of the external power supply. N-type area connected to the negative pole of the external power supply. At this time, you can observe the applied electric field is in this direction. The internal electric field is in this direction. The two are opposite, which means that the external electric field weakens the internal electric field. In this case, it will break the original dynamic balance of the PN junction, so that the diffusion motion of majority carrier is greater than the drift motion of minority. When the applied voltage gradually increases, the diffusion of the majority carrier will form a positive current ID. At this time, the PN junction is turned on. That is, when a forward voltage is applied, a current flows through the PN junction. It's on. Let's take a look at the reverse characteristics. Apply reverse voltage. That is, the P-type area is connected to the negative pole of the external power supply. N-type area connected to the positive pole of the external power supply. At this time, the direction of the external electric field and the direction of the built-in electric field are the same, all in this direction. In this case, the barrier becomes wider. It will make the drift movement of the minority carrier strengthen and further prevent the diffusion motion. So the drift motion of the minority carrier is greater than the diffusion motion of the multiple carrier, so that the original dynamic balance of the PN junction is broken. In this case, the drift of the minority carrier forms a reverse current IS. But one thing about P-type semiconductors and N-type semiconductors, the concentration of the minority carriers in them is very low. The current formed by the drift of the minority carrier is also very weak. We call it the reverse saturation current IS. As the applied reverse voltage increases, this current will basically not increase because the carrier concentration is very low. So at this time, we think that this weak current is not enough to make the PN junction conductive. That is, it is due. So its reverse characteristic is like this. When a reverse voltage is applied to the PN junction, it is off. Let's summarize. When the PN junction is applied with a forward voltage, it has a large forward diffusion current. It is formed by many majority carriers. At this time, the PN junction is low and the low resistance PN junction is turned on. When a reverse voltage is applied to the PN junction, there is only a small reverse saturation current, which is a current formed by the minority carrier. At this time, it shows a high resistance PN junction cutoff. So the PN junction has unidirectional conductivity. For the volt-ampere characteristics, we can use the following exponential function to express. I is equal to Rs times E times the power of V is raised to the power of Vt minus 1, where Rs is a reverse saturation current. The Vt here is 26 microvolts, which is the thermal voltage we just talked about. This formula can be further simplified. When a forward voltage is applied to the PN junction, that is, when V is greater than 0, or V is much greater than Vt, I increases as V increases. If V is much greater than Vt, at this time, V is higher than Vt power, far greater than 1, so we can ignore 1. The formula is simplified as I equals Is times E raised to the power of V compared to Vt power. In other words, it is an exponential relationship. When a reverse voltage is applied to the PN junction, that is, V is negative, if the absolute value of V is much greater than Vt. The above formula can be simplified to I equals negative Is, because the V of E is approximately 0 than the power of Vt. The content in brackets is probably -1. So I is approximately equal to -Is, which is its volt-ampere characteristic, can be expressed by formula. We can also use the volt-ampere characteristic curve to describe. Take a diode made of silicon as an example. Its volt-ampere characteristics can be seen from the picture. When V is greater than VD on, VD on is actually the built-in potential difference VB we talked about before. VD on is here used to refer to the turn-on voltage of a diode or PN junction. When the applied voltage of V is greater than this turn-on voltage, the built-in potential difference is overcome. The current obviously has a value. When V is less than VD on, is less than the turn-on voltage. PN junction is closed. We think the current value is very small. No current flows. For silicon materials, its turn-on voltage, VD on, is usually considered to be 0.7 volts. The PN junction VD on made of germanium material is equal to 0.25 volts. Let's take a look at the breakdown characteristics of PN junction. When the reverse voltage applied to the PN junction increases to a certain value, the reverse current flowing through the PN junction will increase sharply. The reverse voltage will remain basically unchanged. In other words, when the PN junction breaks down in reverse after applying a reverse voltage breakdown, then its voltage will not change anymore. It's basically unchanged. This is called PN junction breakdown. When reverse breakdown, the current on the PN junction is too large. If it takes too long to cause overheating, thermal breakdown will occur. Try to avoid burning the tube. There are two ways to break down the PN junction. One is avalanche breakdown. One is Zener breakdown. Due to its breakdown characteristics, we can make the diode into a Zener diode. Let's see, because once the PN junction breaks down, although its reverse current increases sharply, the voltage across the PN junction remains almost unchanged. Using this feature, we can make Zener diode. Let's take a look at some of its parameters. Look at the picture on the right. Above is a symbol of Zener diode. On the basis of diodes, its symbol is such a structure. We can see from its volt-ampere characteristics that when the applied voltage applied by the diode is approximately Vz, the diode breaks down. At this time, its reverse current increases sharply, but its voltage is almost constant, which is Vz. Zener diode has a working current range, which is its stable current Iz. Usually this current has a minimum value. The current of Iz minimum should ensure that the diode is in a state of breakdown, to ensure that it can penetrate. Another upper limit of the current range is Iz max, which means that the working current of the diode cannot exceed this value. It may burn out if it exceeds this value. Therefore, the working current of the diode should be between these two currents. We call it the stable current Iz. In the reverse breakdown zone, the stable working voltage Vz is this value. Vz is one of the main bases for our selection of regulators according to requirements. This is one of its main parameters. Okay, our breakdown characteristics of diode, just to introduce here. Let's take a look at the temperature characteristics. The volt-ampere characteristic curve on the left, which contains two. One is at T2 temperature. One is the volt-ampere characteristic curve drawn at T1 temperature. We can see that the temperature of T2 is higher than the temperature of T1. As the temperature rises, that is, when the curve transitions from T1 to T2, the forward current will increase from T1 temperature to T2 temperature. If the applied voltage is unchanged, the forward current will increase. As the temperature rises, we can see that the turn-on voltage becomes smaller. VD on becomes smaller. If the temperature increases by 1 degree, VD on decreases by about 2.5 microvolt on average. Another point is that as the temperature rises, the reverse saturation current Is increases. Every time the temperature rises by 10 degrees, Is will double. So from this, we can see that as the temperature increases, Is doubles. Let's introduce the capacitance characteristics of PN junction. The capacitance characteristic is only shown when the PN junction power is changed. Then we have to analyze it in two cases. First, look at the barrier capacitance, CT, when a reverse voltage is applied to the PN junction. Let's look at the picture below. PN junction applied a reverse voltage. At this time, in the process of volt change, the PN junction is similar to a flat capacitor. Because the space charge region of the barrier layer on both sides of the interface, it stores equal values, charges of opposite polarities. When the applied reverse voltage keeps changing, the width of the barrier layer also keeps changing, which is the charge stored in the PN junction. The amount of charge changes accordingly, which is equivalent to the charge and discharge of the plate capacitor. The capacitance characteristic shown at this time is called the barrier capacitance, which is described by CT. The calculation formula of CT doesn't need to be memorized. We probably know about this feature. Let's look at the second capacitance characteristic of PN junction, diffusion capacitance. We use CD to describe the diffusion capacitance. When the PN junction is applied with a change of forward voltage, it shows a kind of capacitance characteristic. Let's take a look at the picture on the right. On both sides of the PN junction, the number of this minority carrier accumulated will also change to a certain extent as the diffusion of majority carriers. The following is a curve of this concentration change of the minority. We see that the closer to the PN junction or the barrier layer, the higher the minority carrier concentration. Because when the applied voltage continues to change, the diffusion current continues to change. So the diffusion of majority carriers will also make outside of the barrier. That is, the concentration of the minority carriers in the neutral zone constantly changing. This is also equivalent to the charging and discharging process of the capacitor. This capacitance characteristic is caused by majority carrier diffusion, so it is called diffusion capacity and is expressed by CD. When a reverse voltage is applied, CD is almost zero. That is, when the forward voltage changes, it can appear as a diffusion capacitor. For the capacitance of the PN junction, we use Cj to describe. The total capacitance is Cj. It is equal to Ct plus Cd. When Y plus positive voltage, this Cd is much larger than Ct. So the capacitance of the diode mainly appears as a diffusion capacitor. Cj is approximately equal to Cd. When reverse voltage is applied, Ct is much larger than Cd. So the capacitance characteristic at this time is mainly represented by its barrier capacitance. Cj is approximately Ct. Apply the capacitance characteristics of PN junction. We can make a varactor diode. Varactor diodes can usually be used for electrical turning of resonant circuits and voltage-controlled oscillators and frequency modulation. This is a PN junction, its formation process, and various characteristics of the PN junction. Okay, that's all for today's lesson. Thank you all.